It is 2 a.m. on a Friday. Your friends went out, but not you. You open your favorite browser, you type netsekviz.net, and hit enter. The page loads in 200 milliseconds. Feels instant. Or at least faster than my girlfriend at choosing dinner. It is not. In that one blink, your computer interrogated a global directory, found a stranger's machine on the other side of the planet, demanded it prove who it was, agreed on a secret that nobody watching the wire could ever read, and pulled back a whole document. All of it, faster than your favorite hacker can scream, "I'm in." Now let's slow that down about 1000x and watch every single step of how one address becomes a page on your screen. Let's follow one request, from your keystroke to the pixels, and crack open every machine it touches. It all starts with what you typed. That is a URL, a Uniform Resource Locator, which is just a fancy address with different parts. HTTPS is the scheme, the rules for the conversation. netsekviz.net is the host, the name of the machine you want. And anything after the slash is the path, the specific thing you want from the host. Your browser looks at that and has a small panic, because it does not actually know where netsekviz.net is. Computers do not route by name, they route by numbers. So before anything leaves your laptop, the browser has to answer one question. What is the IP address for this name? Here comes almighty DNS, the domain name system. DNS is the phone book of the internet. You give it a name, it gives you back a number, an IP address, which is the actual location of the machine. But your browser is lazy, not exactly like me on a Saturday morning, but in the best way. It checks its own memory first. Seen this name recently? Use the saved answer. Nothing there? It asks the operating system, which has its own little cache. Still nothing? Now it goes out to the network, to a recursive resolver, usually run by your ISP or something like 8.8.8.8. Recursive just means this server will do the whole lookup for you and call you back. So just relax. If the resolver has never heard of the name either, it goes on a little quest. It asks a root server, the top of the chain. The root does not know the answer, but it knows who handles .net, so it points down to the TLD server, the one in charge of that whole top-level domain. The TLD server does not know the exact answer either, but it knows who is authoritative for netsekviz.net, the one server that holds the real record. That authoritative server finally hands back the IP after a brief sequence of hot potato. Root to TLD to authoritative. 3 hops to turn a name into a number. And here's the thing everyone gets wrong. This almost never happens in full. Every answer comes with a TTL, a time to live, a little expiry timer. Until it expires, everybody caches it. Your browser, your OS, the resolver. So most of the time, this entire planetary scavenger hunt gets skipped and you get an answer in a millisecond from a cache 2 feet away. Stop and appreciate that. Your browser just found a specific machine out of billions anywhere on Earth before you lifted your finger off the key. If watching the invisible machinery run is your kind of thing, subscribing and leaving us a like is how you get the next one. Okay, back to it, because now we have an IP and a new problem. You have the server's address. You cannot reach it, not directly. Your laptop can only physically hand data to its neighbors, the other devices on your local network. The server in this story is not your neighbor, it is across the internet. So your packet, which is just a chunk of your request wrapped up with addresses on it, has to go to the one device that has a door to the outside world, your router, also called the default gateway. But to hand the packet to the router, your laptop needs the router's hardware address, its MAC address, a serial number burned into the network card, and it might not know it yet. So like a mad dog, it shouts to the entire local network with a protocol called ARP, Address Resolution Protocol. The shout is basically, who has 192.168.1.1? Tell me your MAC. The router answers, that is me. Here is my hardware address. Now your laptop knows exactly where to physically send the packet. So the packet goes to your router, and your router sends it to the next router, and the next, hopping across the internet toward that IP. Your computer never talks straight to the server. It is routers, all the way down. Now the packet arrives at the server. But before either side sends real data, they need to agree they are even talking. That is TCP, the Transmission Control Protocol, the part that makes a connection reliable, so nothing arrives scrambled or missing. It opens with a 3-way handshake. Your browser sends a SYN, which just means synchronize, I want to talk. The server replies SYN-ACK, I hear you and I want to talk too. Your browser fires back an ACK. Great, we are on. 3 little packets, and now there is an open, reliable pipe between your laptop and a machine you have never met. Cool. But an open pipe is not a private one. Anybody sitting on the wire in between can read every byte. So before we send anything that matters, we make it unreadable. This is TLS, Transport Layer Security, the S in HTTPS, and the reason for the little padlock. Here's the naive way to do encryption. Take a secret key, send it to the server, then scramble everything with it. The problem is obvious. If you send the key across the wire, anyone listening just grabs the key and reads everything. Useless. So TLS does something that genuinely feels like magic the first time you see it. Your browser and the server each generate half of a puzzle. They swap only the public halves out in the open, then each side mathematically combines its own private half with the other side's public half, and they both arrive at the exact same secret, a secret that was never, at any point, sent across the wire. That trick is a Diffie-Hellman key exchange, and it is one of the most beautiful ideas in all of security. Along the way, the server also shows its certificate, basically an ID card signed by a trusted authority, so your browser can check it is really talking to netsecviz.net and not an imposter. Certificate checks out, shared secret derived, padlock closed. From this moment on, everything is encrypted. And here's the part the pros care about. Because that shared secret is built fresh from those throwaway puzzle halves, it has forward secrecy. Suppose an attacker recorded every single encrypted byte tonight, saved it, and then a year from now, they steal the server's private key. They still cannot read tonight's traffic. The key that locked it was never stored and never sent. It existed for one conversation, and then vanished. That is the difference between encrypted and bulletproof in hindsight, and modern TLS gives you the second one by default. All of that just to ask a question. Now, through the encrypted pipe, your browser sends the actual request. This is HTTP, the Hypertext Transfer Protocol, and the request is shockingly small. One line, get, / translation. Give me the thing at the root path, plus a few headers, little labels like which host you want and what kind of content you can accept. The server reads it, does its work, and answers. Status code 200, which means, okay, here it is, more headers. And then the body, the actual HTML, the raw text of the page. Your browser asked one polite question and got a document back. Almost home. Quick gut check. We just did 2 handshakes back to back. TCP to make the connection reliable, then TLS to make it private. That is 2 full round trips, 2 there and back journeys across the planet before you have even asked for the page. The newest version of the web looked at that and said too slow. It is called HTTP/3, and it runs on a protocol called QUIC. Instead of stacking TLS on top of TCP, QUIC folds them into one and runs on UDP, a leaner way of firing packets that skips TCP's setup ceremony. Reliability and encryption get negotiated together, so the whole setup collapses from 2 round trips down to 1. And if you have been to the site before, it gets greedy. A feature called zero round trip time, or 0RTT, lets your browser send encrypted data in the very first packet, using a secret it remembered from last time. No handshake at all. That is a big part of why the modern web feels so much snappier than it did a few years ago. That document your machine just begged for is just text. Your screen needs pixels. So the browser runs a pipeline. It reads the HTML and builds the DOM, the document object model, a tree of every element on the page. It reads the CSS, the styling rules, and builds a matching tree called the CSSOM. It then combines the two into the render tree, which holds only the things you can actually see. Then it runs layout, doing the geometry, figuring out where every box goes and how big it is. Then paint, filling in the actual pixels, the colors, and text and borders. And for the smooth stuff, it hands layers to Big Brother, the GPU, to composite together. And it does not even wait for everything. It paints what it can as fast as it can, then fires off more requests for images, fonts, and scripts, each one quietly kicking off its own little version of this entire journey. So, you typed a name. Your machine turned it into a number, found a path to a stranger's server, opened a reliable pipe, agreed on an unbreakable secret with math, asked one question, and painted the answer onto glass. Routers, resolvers, handshakes, and key exchanges. Dozens of machines, 1 keystroke, 200 milliseconds. It only feels like magic because it is invisible. Now you've seen it, go touch some grass and see you in the next one.